Hello everyone, my name is Lai Yupeng, and today I will be presenting a fundamental pillar of mathematical analysis, the Archimedes property of real numbers. First, let's start with the introduction. It is named after the Greek mathematician Archimedes of Cyprus, and its intuitive idea is no matter how small positive quantity we given, we can exceed any large quantity by repeatedly adding a smaller one, and it distinguishes the real number system R from fields containing infinitesimals. As you can see in this diagram, if we have a tiny and a huge, we can always find a number of steps such that times is greater than. This simple observation is what distinguishes our real numbers from other systems that might contain infinitesimals, numbers so small they can never add up to a normal size. Now let's start with the definition. The Archimedes property can be stated in several equivalent forms, but in this presentation I only state two definitions in our textbook. The definition 1 is for any positive n in R, there exists a positive integer n in n such that n bigger than n. And the definition 2 is for any positive number epsilon bigger than 0, there exists a positive integer n in n such that 1 over n less than epsilon. Now let's prove it. For definition 1, as in class, we prove by contradiction. First, we assume there exists a positive n such that for n in n, n less than n, and this implies that m is an upper bound of the set of natural numbers. But we know from completeness axiom n is not bounded above in R. So let's make a contradiction. Therefore, there doesn't exist a positive n such that for all n in n, n less than n. So the statement 1 is true. Next, we try to prove statement 2 using statement 1. From statement 1, we know that there exists n bigger than 0, such that m bigger than n, and we in statement 2 we let epsilon bigger than 0, and we define m equals to 1 over epsilon. By statement 1, we can know that there exists n in n such that n bigger than 1 over epsilon, and we rearranging the inequality, we get n epsilon bigger than 1, so 1 over n less than epsilon, and we prove statement 2. And let's talk about the significance of the theorem. Why is the theorem so important? First, it provides the link between discrete integers and continuous real numbers. Second, it allows us to prove the density of rationals, which means rational numbers are everywhere on the number line. Most importantly, it is the bedrock of the definition of limits, the language of calculus, ensuring that there are no infinitely small gaps in our number systems. Let's talk about some example of how to use the Archimedes property to solve the problem. The first example is limit of sequence. We should show that limit n to infinity 1 over n equals to 0. From class, we know that the definition of limit of sequence is for all epsilon bigger than 0, there exists n bigger than 0. For all n in Z class, n bigger than n, the limit n goes to infinity 1 over n minus 0 less than epsilon. We need to show this. We need to show this one. So we first assume that epsilon bigger than 0 and n bigger than big N, such that 1 over minus 0 less than epsilon is what we want. And by the Archimedes property, we can always find an n such that 1 over n less than epsilon. And for all n bigger than n, we can find 1 over n less than or equal to 1 over big N and less than epsilon. So we can prove this. Okay, for the next example, we first have a theorem between any two real numbers a and b, where a less than b, there exists a rational number r in Q such that a less than r less than b. And we need to prove the density of a rational. It means that for any a and b in R, the interval AB must exist a rational number. So we should prove this, and we let epsilon equals to b minus a. By the Archimedes property, there exists n in n, such that 1 over n minus b minus a. 1 over n minus b minus a. And we can know that n b minus a equals to n epsilon bigger than 1. We know this, and we know that the interval na and b, the interval NAB length is NB minus NA 等于 NB minus A. Its length is bigger than 1, so it must contain at least one integer n from previous theorem. So we can know that NA less than n less than NB, and we divide n on both sides, we can get a less than m over n less than b. We know that m and n is in R, so that m over n is a rational number. Since n less than m over n less than b, the rational number must in the interval AB. So we prove for all intervals in R, there must exist a rational number. And in conclusion, the Archimedes property is essential for higher level mathematics. It's much more than a simple observation about counting. It is an essential tool that gives us the power to understand limits, continuity, and integration. Without it, the rigorous study of mathematical analysis would not be possible. And thank you for your time and for watching this presentation.